This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas.
So, imagine you're tasked with writing one of those choose-your-own-adventure books.
Oh, like the ones from when we were kids?
Yeah, exactly. You know the ones.
Yeah.
You read a few pages, the tension is building, and then suddenly you hit the bottom of the page and you've got a choice.
Right, like if you want to open the mysterious iron door, turn to page 42.
Exactly. Or if you want to run away into the dark forest, turn to page 73. And the thrill was always in knowing that your specific decision dictated the entire reality of the next few chapters.
Yeah, you felt like you were in control of the universe.
Right. Only in this specific book that you're writing, the main character isn't like a wizard or a space explorer. The main character is planet Earth.
Okay, high stakes.
Very high stakes.
Yeah.
The plot is the next 500 years of the global climate. And the ending that you eventually turn to determines the physical fate of humanity.
Wow.
So as the author, how do you even begin to decide which paths are worth writing down? Because you can't write every single possible future into the book, right?
No, I mean, it would be infinitely long.
It would be chaotic.
Yeah.
And completely useless to the reader. You have to choose the most important paths. You have to essentially define the boundaries of what could actually happen.
Right. You need a highly structured framework.
Yeah.
A set of bounded, deeply researched narratives that capture the most critical bifurcations we might face as a global society.
Right.
Like, you can't include a page where, I don't know, an asteroid hits the Earth or aliens come down and scrub the carbon out of the atmosphere.
Because that's not exactly helpful for us right now.
Exactly. Those aren't useful parameters for human decision-making. You need pathways that reflect the hard limits of our atmospheric physics, the complex gears of our macroeconomics, and, frankly, the messy realities of our geopolitical systems.
Well, today, for this deep dive, we are opening up the ultimate blueprint for that exact book. We're diving into a 2026 scientific paper published in the journal Geoscientific Model Development.
A very light read.
Oh, yeah, super breezy. It's titled The Scenario Model Intercomparison Project for CMIP7, which scientists just call ScenarioMIP.
Right.
And I know it sounds incredibly dense, like a bureaucratic mouthful of acronyms, but what we're looking at here is quite literally the foundational script for our future.
It really is. It's the architectural blueprint for the scenarios that will drive the world's most sophisticated climate models for the next decade.
Which means it's not just an academic exercise.
Oh, not at all. The math generated by the protocols in this paper, it will feed directly into the upcoming reports from the Intergovernmental Panel on Climate Change. But, its reach goes way beyond that.
How so?
Well, this specific framework will guide international treaties. It's going to dictate the baseline algorithms that central banks use to assess systemic climate risk hiding in our financial systems.
So it affects money, like real money.
Absolutely. When your local municipality decides how high to pour the concrete for a new coastal seawall, or when your insurance provider recalculates the flood risk premium on your 30-year mortgage.
Wait, really? My mortgage?
Yes. The underlying risk models are tracing their lineage right back to the 7 specific scenarios outlined in this exact document.
That is wild. So our mission today is to crack open this blueprint. We want to look at the specific scripts, these 7 meticulously crafted adventures that scientists have written for us, and understand the mechanics of how they actually simulate tomorrow.
It's a huge undertaking.
It is. And to predict the future of a system as complex as the entire Earth, I found myself wondering where researchers even begin. You don't just open a laptop and type, what will the weather be in 2080?
Right, if only it were that simple.
Reading through the methodology of this paper, it becomes really clear that predicting the future requires stringing 2 completely different types of computational brains together.
Yeah, you're looking at the critical handoff between the human world and the physical world.
Okay, break that down for us.
So the first brain in this operation is the suite of integrated assessment models, the IAMs.
IAMs.
Yeah, so these are the socioeconomic engines. They're designed to simulate human behavior at a planetary scale.
Human behavior? Like how?
Well, they ingest massive data sets on global demographics, right?
Right.
They project population curves across different continents. They model macroeconomic economics, tracking GDP growth, the fluctuating prices of commodities, the learning curves of new technologies.
Okay, so it's a massive economic simulator.
Exactly. They calculate whether a simulated society will find it cheaper to, say, build a massive offshore wind farm or a natural gas plant in the year 2040. And they base that on assumed carbon taxes and fuel prices.
Wow.
Their entire job is to crunch the chaotic math of human civilization and spit out a highly specific schedule of land use changes and greenhouse gas emissions.
So if we go back to the movie analogy, the socioeconomic models, the IAMs, they're essentially the screenwriters.
That's a good way to put it.
They're sitting in a writer's room debating the plot based on human motivations. They decide, okay, in this timeline, humanity gets its act together, we build 2 billion electric vehicles, and we phase out coal. Or, conversely, in this timeline, humanity fractures, trade wars erupt, and we chop down half the Amazon rainforest to plant soybeans.
Yeah.
They write the script of human action.
Yes, exactly.
But knowing that a simulated society emitted 40 gigatons of carbon dioxide doesn't tell you if a hurricane is going to hit Miami.
No, it doesn't. And that is where the second brain comes in.
Okay.
That requires the Earth System Models, the ESMs.
So we have IAMs writing the script and ESMs.
The ESMs are the physical actors forced to perform the script, and they do not care about our economics.
They don't care that wind was cheaper than coal.
Not at all. They don't care about human intent or political treaties. The ESMs are pure engines of physics, chemistry, and biology.
Just raw science.
It's raw physical laws.
Yeah.
They take the raw emissions data handed to them by the IAMs, and they apply the fundamental laws of thermodynamics and fluid dynamics.
What does that actually look like in a computer?
Well, they break the Earth's atmosphere and oceans down into millions of three-dimensional grid boxes.
Like Minecraft.
Basically, yeah. But a hyper-complex Minecraft that calculates the transfer of heat, moisture, and momentum between every single box every few simulated minutes for decades.
Oh, wow.
Yeah. They simulate the slow march of ocean currents, the formation of clouds, the chemical buffering of the oceans, the melting of the ice sheets. They show us the inescapable physical consequences of the script.
Okay, so this deep dive today is entirely about that script writing phase. ScenarioMIP is the governing body deciding what those scripts should be before they hand them over to the supercomputers running the physics engines.
Right.
And this brings us to a really massive shift in the scientific consensus, because this new protocol is CMIP7, which obviously implies there was a CMIP6.
Yeah, that's how numbers work.
Right. And in that previous generation, the CMIP6, there was one particular script that completely dominated the global conversation.
Oh, definitely.
Like every time you saw a terrifying headline warning of unlivable heat or boiling oceans by the end of the century, it was almost always tracing back to one specific worst-case scenario from CMIP6.
SFP5 8.5. It's exactly. But according to this new blueprint we're looking at today, that apocalyptic worst-case scenario has been officially killed off. It's just gone from the core menu.
Yeah, the scientific community had to adapt to how rapidly human reality actually outpaced the models.
Really? Outpaced how?
Well, when the CMIP6 scenarios were being designed and debated, which was roughly a decade ago, SSP5 8.5 was constructed as the high-end unmitigated emissions pathway.
The darkest timeline.
Right. It was built on a socioeconomic storyline where the world effectively abandoned environmental concerns, experienced massive economic growth, and fueled that growth almost entirely by returning to coal.
Just burning all the coal.
All of it. It assumed a vast, aggressive expansion of fossil fuel infrastructure throughout the entire 21st century. And, looking at the geopolitical and technological trajectory of the early 2010s, that storyline was deemed a plausible upper boundary of risk.
But then the 2010s ended, and the global energy market fundamentally fractured that storyline.
It really did. Because I was looking at the underlying cost assumptions that built that old scenario. It assumed coal would remain the absolute cheapest, most dominant fuel source forever. But it completely missed the sheer velocity of the renewable energy revolution.
Nobody saw it coming quite that fast.
Over the last decade, the levelized cost of energy for solar and wind power absolutely plummeted. And the learning curves for lithium-ion batteries accelerated way past the most optimistic projections, which brought electric vehicles into mass market viability.
And alongside the technology, the diplomatic landscape shifted too. I mean, the Paris Agreement happened. Policies were actually codified.
So the real world just drifted away from that worst-case model.
Right. I mean, we are still nowhere near the emission reductions required to stabilize the climate safely. Let's be clear about that.
Yeah.
But the baseline structural economics of the energy market have irrevocably shifted.
It just doesn't make financial sense to build coal anymore.
Exactly. It simply no longer makes macroeconomic sense to build the colossal, globe-spanning coal infrastructure that SSP 5 8.5 required. The market forces just won't support it, even in the absence of stringent climate policies.
Because renewables are just cheaper.
Yeah. Because of this, a future where we regress and burn those unimaginable quantities of coal is no longer analytically sound. So, for the CMIP7 design, the researchers evaluated that old worst-case scenario against current data and officially classified it as implausible.
And that word right there, implausible, that brings us to a fascinating epistemological debate right in the middle of the source material.
Oh, the plausibility debate.
Yeah, box 1 of the paper is entirely dedicated to defining the concept of plausibility. And reading through it, I realized what the authors are deliberately avoiding. They're designing the blueprints for the global economy.
Yeah.
They completely refuse to use the word probability.
They hate that word.
They never look at a scenario and say, there is a 40% chance we follow this path and a 10% chance we follow that one. They strictly categorize the futures as either plausible or implausible.
Right.
And I'm struggling with this a bit. Because if I'm a policymaker betting trillions of dollars on infrastructure, or if I'm a banker assessing systemic risk, plausibility feels dangerously vague.
It's very squishy for an economist.
Right. If you are going to tell me to restructure the global energy grid, why won't the models just give me the hard statistical odds of the different futures?
Well, it is a profound frustration for policymakers, I'll give you that, but it is a scientifically vital boundary to maintain.
Why?
Because if a scientist gives you a probability, say a 60% likelihood, it implies that they possess a complete statistical distribution of all possible outcomes.
Like knowing there are exactly 52 cards in a deck.
Exactly. If you know the deck, you can calculate the exact odds of drawing an ace. But the future of human society is not a deck of cards. It is a deeply complex, chaotic system governed by human agency. Assigning concrete probabilities to a climate scenario requires assigning mathematical odds to future political choices.
Oh, I see. You'd have to calculate the statistical probability of a specific politician winning an election in the year 2032.
Right.
And the exact probability that their specific coalition will successfully pass a carbon tax.
Which is obviously impossible. If researchers claim they can predict the volatility of human elections or geopolitical conflicts or sudden technological breakthroughs with a neat percentage, they are abandoning rigorous science for fortune-telling.
So they stick to plausibility.
Yes. Plausibility is a different metric entirely. A plausible scenario simply means there is a rigorously tested causal pathway that aligns with our current understanding of technological limits, economic principles, and physical laws.
It just means it could happen.
It means the scenario does not require magic, and it does not violate the laws of physics. By bounding the edges of what is physically and economically possible, from the darkest backsliding to the most optimistic coordination scientists, provide a comprehensive map of the terrain.
They aren't telling you which path you will take.
No, they aren't predicting which path humanity will walk. They are illuminating the entire landscape so society can make an informed choice about which way to steer.
That reframing really changes how you read the rest of the document. We aren't looking at predictions, we're looking at the boundaries of the canvas.
Exactly.
So let's explore that canvas. Let's look at the Magnificent Seven, the core 21st century scenarios that will define CMIP 7. Rather than just reading a list, I noticed the researchers structured these 7 futures around specific narrative tensions.
Yeah, they group them conceptually.
Let's start by looking at the upper boundary. If the old coal apocalypse scenario is dead, what is the new ceiling of our plausible failures?
The designers categorize the new upper boundary under what we might call the backsliding group.
Yeah,
These are the scenarios where current progress just stalls and reverses. The highest of these is simply called the high emission scenario, or H. It replaces that old SSP 5 8.5 as the new ceiling.
What's the story there?
The narrative driving the H scenario is a structural rollback of our current climate policies. You have to envision a geopolitical landscape defined by a severe resurgence of nationalism and isolationism.
So a world where international cooperation fractures.
Exactly.
Countries retreat behind their borders. They hoard critical minerals required for battery manufacturing. The supply chains for green technology completely break down.
And governments actively dismantle the environmental regulations they passed in the 2020s to focus entirely on short-term fossil fuel domestic security.
Okay, so it represents a systemic failure of global governance. It's not just business as usual. It is a proactive deviation from the positive trends we're currently seeing.
Right. It establishes the absolute highest volume of greenhouse gases we could plausibly force into the atmosphere given today's economic realities.
But the variation of this scenario is what I found truly fascinating. There's a second scenario in this upper group called the high to low scenario, HL.
Oh, this one is really interesting.
Yeah, reading the socioeconomic narrative of HL, it struck me as the most deeply human, psychologically realistic response in the entire paper.
It definitely hits close to home.
In the HL storyline, we follow that exact same high-emission, isolationist path. We ignore the environment, we burn the fossil fuels, we build the walls. We do this for decades, right up until the middle of the century.
And then,
Around 2050 or 2060, the physical impacts of climate change, the crop failures, the coastal flooding, the heat waves become so catastrophic and undeniable that humanity experiences a collective global panic.
the narrative assumes a sudden extreme awakening.
Yes, it's the ultimate procrastination scenario.
Oh, totally.
It's the geopolitical equivalent of a university student who skips every lecture, ignores the reading, and plays video games all semester. Then, 3 days before the final exam, they look at the syllabus, realize they are about to fail out of school, and they stay up for 72 hours straight on a cocktail of espresso and adrenaline, cramming a semester's worth of knowledge into a long weekend.
I think we've all been there.
Right. The HL scenario is humanity cramming for the final exam. We panic in 2060, and we initiate radical emergency mitigation efforts, pulling every conceivable technological and economic lever to somehow force our emissions down to net zero by the year 2100.
It is a vital scenario to model because, realistically, delayed action is a very common political dynamic.
Yeah, that's what we usually do.
But the scientific value of running the HL scenario through the Earth system models is discovering the physical toll of that procrastination.
What happens when you cram?
Exactly. If you wait until 2060 to panic, you have to execute an economic miracle in 4 decades. But more importantly, the physics engine might reveal that cramming doesn't work for the climate.
What are the consequences of letting the planet heat up that much before you hit the brakes?
By the time humanity wakes up in 2060, the Earth system might have already crossed irreversible tipping points. The permafrost might already be thawing. The ice sheets might already be committed to collapse.
So you might pull an all-nighter to study for the exam, only to realize the exam has already been graded.
Unfortunately, yes.
Moving down from the backsliders, we reach the middle of the canvas, the status quo group. This is where we assume no sudden panics and no major regressions, just the inertia of the present moment.
The core of this group is the medium scenario, or M, and this serves as a really vital diagnostic tool. In the medium scenario, the socioeconomic screenwriters freeze current climate policies exactly as they exist in the year 2025.
So just to clarify, this acts as a sort of control group for political apathy. It assumes we don't roll back the laws we have, but we also don't pass a single new one.
Exactly. It strips away all the aspirational rhetoric. If a government holds a press conference today and promises to be net zero by 2050, but they haven't actually passed the binding legislation or funded the infrastructure to achieve it,
The medium scenario ignores it.
completely ignores the promise. It only models the laws and taxes that are officially on the books today.
It measures the hypocrisy gap.
Basically, yeah.
It allows scientists to run the physics models and show policymakers the exact physical weather that will result from the gap between the speeches they give and the laws they actually write.
Right. And alongside that is the medium to low scenario, ML, which assumes we eventually start keeping our promises, but we are sluggish about it.
We drag our feet.
We miss the short-term targets of the Paris Agreement. We cruise along on current policies for a while. But as green tech continues to get cheaper, market forces slowly grind our emissions down. We eventually reach net zero by 2100, but we arrive late.
And we've put too much carbon into the air in the meantime.
Which forces the ML scenario to rely heavily on pulling carbon out of the atmosphere later in the century to compensate for our sluggishness. It's a delayed action pathway that relies on future cleanup.
That leaves us with the bottom of the canvas, the overachievers, the scenarios that actually attempt to hit the goals of the Paris Agreement and, save the climate.
The Paris Agreement group includes 3 distinct pathways. The first is the low scenario, or L. This models a highly coordinated, steady global effort. Emissions drop rapidly and consistently, leading to net zero CO2 emissions around 2070.
Okay.
The climate models run this to see if it gives us a high likelihood of stabilizing global temperatures below 2 degrees Celsius of warming. But below that is the very low scenario, VL.
The absolute floor of plausibility.
Yes, the VL scenario is the bleeding edge of what researchers currently deem mathematically and physically possible for rapid decarbonization. It attempts to keep global warming as close to 1.5 degrees Celsius as possible.
But the assumptions required to achieve this are staggering. Right.
Unprecedented. It requires immediate, massive, simultaneous shifts across the entire global economy, starting essentially tomorrow. We were talking about the deep, rapid electrification of heavy industry, massive global build-outs of renewable grids at a scale we've never seen, and crucial, widespread behavioral changes.
And that behavioral element is a massive shift from just relying on technology. The source material explicitly models profound cultural changes.
Yes, it doesn't just assume we invent better machines.
It assumes a massive reduction in global energy demand, not just through efficiency, but through actual behavioral shifts. It models a global transition toward low greenhouse gas diets, specifically referencing things like the Lancet Planetary Diet, which drastically reduces meat consumption.
Right.
The VL scenario isn't just asking, what if we build better solar panels? It is asking, if humanity pull every single technological, economic, and cultural lever available to us, what is the best possible physical outcome we could achieve?
And sadly, even with all those levers pulled, there is a very real possibility that the physical momentum of the Earth's climate will still push us past the 1.5 degree mark anyway.
Because of the inertia.
Exactly. Which brings us to the final, seventh scenario. The low to negative scenario, or LN, this is the overshoot pathway.
Overshoot.
It acknowledges that the window for a perfectly smooth transition might have already closed. In the LN script, we blow past the 1.5 degree target mid-century, but then the socioeconomic models deploy almost unimaginable scales of carbon dioxide removal.
So, vacuums.
Giant vacuums.
Yeah.
We build industries dedicated entirely to vacuuming carbon out of the atmosphere, forcefully dragging the global temperature back down over the ensuing decades.
So we have the full spectrum now, from the isolation backsliders to the apathetic status quo to the utopian overachievers.
That's the Magnificent Seven.
But, as I was reading through how these socioeconomic pathways are constructed, I hit box 2 in the paper.
Oh, box 2, yeah.
It addresses the impartial reality of equity, and it introduces a massive tension between the physical science of these models and the political reality of how climate change is debated on the global stage.
It's a very thorny issue.
Right, because global climate diplomacy is fundamentally rooted in the concept of justice. The argument, which is historically accurate, is that wealthy, industrialized nations in the global north built their wealth by emitting the vast majority of historical carbon.
Yes.
Therefore, developing nations in the global south argue that the wealthy nations must bear the heaviest burden of cutting emissions and financing the transition. That is the core of climate justice. But box 2 explicitly points out that the Earth system models are entirely blind to this concept.
Now, to be clear to the listeners, we aren't taking a side here. The paper itself is making a critical distinction between moral reality and physical reality.
Right, exactly. We're just reporting what the protocol says.
The climate models themselves are impartial. They're designed exclusively to simulate the fluid dynamics and biogeochemistry of the planet. A molecule of methane or carbon dioxide absorbs and re-radiates long-wave infrared radiation with the exact same physical properties regardless of its origin.
The atmosphere doesn't ask for a passport.
Precisely. The Earth system model does not know and cannot calculate whether that molecule was emitted by a billionaire's private jet flying out of London or a subsistence farmer burning brush to clear land in sub-Saharan Africa. The physics engine is deaf to the politics of equity. It only responds to atmospheric concentration and radiative forcing.
Now, to be clear, the socioeconomic models, the screenwriters, they do factor in regional differences, right? They don't assume everyone cuts emissions at the exact same time.
That is correct. The IMMs do incorporate regional economic differentiation. In the ambitious low-emission scenarios, the models assume that high-income nations deploy capital, build renewable infrastructure, and implement carbon pricing much earlier and at much higher rates than lower-income nations.
Because they have the money to do it.
Exactly. This reflects a baseline of economic plausibility regarding who actually has the capital to transition first. But the fundamental point the researchers are making in box 2 is that the ScenarioMIP protocol is not a mathematical solver for global wealth redistribution.
So if a UN diplomat looks at the low scenario and says, excellent, this trajectory keeps us under 2 degrees, the computer is not handing them a treaty that dictates how to fairly divide the economic pain of achieving it.
No.
The computer is simply saying, if the total aggregate volume of global emissions matches this curve, here is the temperature anomaly you can expect.
Yeah.
The massive, messy human fight over who pays the bill is left entirely up to the politicians.
Right. The authors note that researchers who study climate justice should take the outputs of these physical models and combine them with separate sociological research to study just transitions. But the CMIP7 architecture itself remains anchored purely in the physics of the atmosphere.
And how those models calculate that physics is undergoing a total revolution.
Yes, a massive upgrade.
Which brings us to what is arguably the most profound technical leap in the entire CMIP7 protocol. We are not just giving the models new scenarios. We are fundamentally changing the architecture of how the Earth breathes inside the simulation.
The shift to emission-driven runs.
Yes. We are shifting the protocol from concentration-driven runs to emission-driven runs. I want to break this down deeply because understanding this mechanism changes how you view climate predictions entirely.
It really does.
In the past, in CMIP6, the majority of the models were concentration-driven. Let's look at how that actually worked mechanically.
Under a concentration-driven framework, the human models, the IAMs, would calculate all the fossil fuels burned and forests cleared. Then the IAMs themselves would run a highly simplified offline calculation to estimate how much of that carbon was absorbed by the oceans or trees and how much stayed in the air.
Okay.
Finally, they would hand the supercomputers running the physics engines a simple predetermined timeline of atmospheric CO2 concentrations. They effectively bypass the Earth's interactive carbon cycle.
They just program the physics engine with a mandate.
Exactly. They'd say, in the year 2060, the atmosphere contains exactly 480 parts per million of CO2. Now, calculate the temperature and the weather.
The analogy that came to mind when reading this is like a health and fitness app. A concentration-driven model is like an app where you just manually type in your final body weight.
That's a great way to put it.
You open the app and type, I weigh 180 pounds today, and the app runs a static calculation to tell you your body mass index and your general health risks. It doesn't ask you what you ate for breakfast. It doesn't ask if you went for a run. And it doesn't care about your genetic metabolic rate.
Right. It just takes the number.
It just takes the final number you handed it and runs the basic math.
It's an effective way to save computational power, but it leaves out the entire biological reality of the system. For CMIP7, the focus is shifting heavily to emission-driven scenarios.
Okay, so what changes?
Under this new protocol, the human models do not calculate the final atmospheric concentration. They only hand over the raw, gross emissions. They tell the Earth system model, humanity just pumped 40 gigatons of CO2 into the air this simulated year, and we chopped down this specific grid of forests in the tropics.
So now, returning to the app analogy, you can't just type in your weight. You have to log every single calorie you consume.
Every single one.
You log the pizza, you log the salad, you log the 30 minutes you spent on the treadmill, and the app actually contains a highly complex, dynamic simulation of your digestive tract, your insulin responses, your basal metabolic rate, and your gut microbiome.
Now that would be a complicated app.
Right. The app has to simulate the entire metabolic process to figure out how your specific body breaks down those calories, and then the app tells you what the scale will say at the end of the week.
Precisely. The Earth system model is now forced to simulate the entire planetary metabolism, and the Earth's metabolism is staggering in its complexity.
What does that have to calculate?
Well, the ESM has to simulate the ocean's solubility pump. That's the physical chemistry of cold water dissolving carbon dioxide and sinking it into the abyss. It has to simulate the biological pump phytoplankton blooming, absorbing carbon, dying, and snowing down to the ocean floor.
And what about on land?
On land, the model simulates photosynthesis. It actually calculates the opening and closing of microscopic stomata on the leaves of billions of simulated trees, calculating how much CO2 they breathe in based on the simulated humidity and soil moisture.
And it has to simulate the decay too, right?
Yes.
Yeah.
It has to model the permafrost thawing in the Arctic and calculate the microbial respiration releasing methane back into the air. It has to figure out dynamically how much of that 40 gigatons of human emissions is actually swallowed by the planet and how much is left lingering in the atmosphere to trap heat.
The reason this shift to emission-driven modeling is so vital is that the Earth's metabolism is not static, is it?
Not at all. As the planet warms, its ability to digest our carbon changes.
Oh, right. Because warmer ocean water physically cannot hold as much dissolved CO2 as cold water.
Exactly. As the oceans heat up, their capacity to act as a carbon sink diminishes. If the physics engine simulates a decade-long mega drought in the Amazon basin, the trees stop growing, photosynthesis slows down, and the rainforest starts absorbing carbon.
And if you just prescribe a static concentration pathway, like the old models did, you're blind to that.
You miss it entirely. You are blind to these chaotic, nonlinear feedbacks. By running emission-driven models, we are allowing the Earth to interact with our pollution in real time. We might discover that even if humanity follows the strict low-emission pathway, the Earth's degraded, exhausted carbon sinks leave far more CO2 in the atmosphere than we banked on.
We are essentially giving the planet a voice in the simulation. We're letting the Earth vote on how bad things get.
Yes.
And this interactive handoff between the human script and the Earth's metabolism becomes incredibly fraught when we look at how these scenarios plan to clean up our mess. A massive component of the ambitious pathways, like the very low and overshoot scenarios, relies on removing carbon from the atmosphere.
The vacuums we talked about.
Right. But there is a glaring disconnect between what the economists are writing in the script and what the climate models can actually simulate. Let's look at the carbon removal conundrum. We have to start with BCCCS.
BECCS. It stands for bioenergy with carbon capture and storage.
Okay, what is that practically?
It is a technological cornerstone of almost every optimistic climate pathway. The theory behind BECCS is a closed-loop engineering marvel. First, you utilize massive tracts of land to grow bioenergy crops.
Like corn.
More like fast-growing biomass like switchgrass, willow, or specialized trees. As these crops grow, they pull carbon dioxide out of the ambient air through photosynthesis. Once mature, you harvest the biomass and transport it to a specialized power plant where it is burned to generate electricity.
But wait, if you burn it, doesn't the carbon just go right back into the air?
Normally, yes, but crucially, in BECCS, you do not let the exhaust enter the atmosphere. You install advanced chemical scrubbers, often using amine solutions, inside the smokestacks to strip the CO2 out of the flue gas.
Ah, the capture part.
Right. You compress that captured CO2 into a supercritical fluid, pipe it away, and inject it deep underground into porous geological formations, like depleted oil reservoirs or saline aquifers, where it is permanently trapped beneath impermeable cap rock.
So it produces electricity while resulting in net negative emissions. It literally functions like a planetary vacuum cleaner.
In theory, yes.
And the socioeconomic models lean heavily on BECCS. They build massive global industries around it in their scripts to hit the 1.5-degree target. But the source material contains a startling reality check.
Yeah, this was eye-opening.
The researchers surveyed the 19 major Earth system modeling centers, preparing their supercomputers for CMIP7. They asked these cutting-edge physics teams, can your model dynamically simulate a BECCS industry? Can you simulate the specific agricultural yields of switchgrass, the chemical efficiency of the smokestack scrubbers, and the complex fluid dynamics of injecting supercritical carbon into subterranean rock?
And the response was a resounding admission of limitation.
They can't do it.
No. The physics engines are built to model the natural world, not industrial chemical engineering. According to the survey, only 26% of the climate models have the capacity to simulate the complex agricultural dynamics of bioenergy crops. And a mere 11% possess any code capable of computing the carbon capture efficiency of an industrial power plant.
So the actors are looking at the screenwriters handed them and saying, we don't have the props for this scene. We don't know how to act this out.
Basically.
So how do they bridge that gap? If the human model demands the deployment of a magic carbon vacuum, but the physics model lacks the code to simulate it, what is the workaround?
The workaround forces the human models to do the math offline. For BECCS, the IAMs calculate the entire process internally. They figure out how much carbon the bioenergy system captured and stored, and they simply subtract that tonnage from the gross global emissions number.
Oh, they just cheat.
Well, they hand the physics engine a mathematically reduced net emission value. They effectively say to the ESM, here is the final carbon number. Don't worry about the machinery we used to achieve it. Just put this much carbon in the atmosphere.
So the human model just hands over a solved math equation. But what fascinated me is that this is not how it works for planting trees, afforestation. Planting 1 billion trees is also a form of carbon removal, but the models treat it entirely differently than BECCS.
Right, because the Earth system models do understand trees. The physics engines contain highly sophisticated dynamic global vegetation models. They know how to simulate the biological life cycle of a forest.
So how does the handoff work there?
So, for afforestation, the human models do not hand over a solved carbon number. They hand over a geographic map. They provide a gridded, high-resolution dataset of global land use. The IAM says to the physics engine, humanity has decided to abandon these specific agricultural grids in the mid-latitudes, and we want you to grow a deciduous forest on these exact coordinates.
And the physics engine actually has to grow the simulated trees.
Yes.
It has to calculate the soil composition, the available sunlight, the exact amount of simulated rainfall hitting those coordinates, and determine dynamically how much carbon that specific forest manages to pull out of the air.
Exactly. The ESM models the forest as a living component of the Earth system subject to the changing climate.
And this is where I see a terrifying tension brewing in the data. What happens when the human model's ambition collides with the physical model's weather?
This is exactly why we run these models.
Right, because imagine the IM screenwriters write a script where humanity saves itself from tipping points by planting a continent-sized forest, fully expecting it to act as a massive carbon sink. They hand the map to the physics engine. But the physics engine runs the simulation, factors in the warming oceans and shifting atmospheric currents, and subjects that specific geographic region to an intense multi-year mega drought.
This is precisely the kind of nonlinear feedback the scientific community is desperate to understand. The socioeconomic assumption is that the forest is a permanent vault for carbon.
But the reality is much messier.
The physical reality simulated by the ESM might show the forest drying out, the canopy dying back, and then a simulated dry lightning strike ignites the dead biomass.
Oh, wow.
The entire afforestation project burns to the ground. In a matter of days, the carbon sink vaporizes, transforming into a massive carbon source, violently ejecting decades of stored carbon back into the atmosphere.
So we are testing whether our most optimistic plans to engineer our way out of this crisis might violently backfire because we failed to account for the hostility of the weather we've already created.
Yes.
The human ambition crashes headfirst into physical reality, and that tension between what we demand of the Earth and what the Earth can actually physically endure gets pushed to the absolute breaking point when we look at the timeline of these simulations. Because this blueprint does not stop at the end of this century.
No, it doesn't. The timeline extension is a critical component of ScenarioMIP. This brings us to Act 4, the deep future.
It is a profound myopia in our political discourse that almost all climate targets end at the year 2100.
Everyone talks about 2100.
Every treaty, every net zero pledge, every corporate sustainability report frames the year 2100 as the finish line. We must limit warming to 1.5 degrees by 2100. It is treated as if the clock will strike midnight on New Year's Eve in 2099. The credits will roll, the Earth will pack up its atmosphere, and everyone just goes home.
Right, but physics doesn't care about our calendars.
Exactly. And the ScenarioMIP protocol explicitly dictates that several of these scenarios must be extended and run on the supercomputers out to the year 2500, 500 years into the future.
Which is incredibly computationally expensive.
It requires massive amounts of expensive supercomputer time to run models that far out. Why do researchers need to know the temperature anomaly of the year 2350?
Because the Earth system is governed by varying degrees of thermal inertia. If you only look at the timeline up to 2100, you are exclusively studying the fast-moving variables of the climate system.
Like what?
You're looking at surface air temperatures, immediate precipitation changes, seasonal sea ice melt. These variables respond relatively quickly to the concentration of carbon in the air. But the planet is dominated by slow-moving monsters.
Slow-moving monsters.
The massive Greenland and Antarctic ice sheets, the abyssal depths of the global ocean, the Atlantic meridional overturning circulation.
These systems have massive physical mass. They take centuries to fully absorb the heat we are trapping today.
Exactly. Even if humanity executes the perfect very low scenario and we completely cease emitting greenhouse gases by 2070, the thermal momentum is already locked in.
The planet just keeps reacting.
The surface temperature might stabilize, but the deep ocean will continue to absorb heat and physically expand thermospheric sea level rise for centuries. The ice sheets, having been destabilized by the 21st century warming, will continue to calve and melt, raising sea levels inch by inch, decade after decade, long after the emissions have stopped.
So we need to look further ahead.
The scientists who study multi-century irreversibility, the researchers tracking species extinction rates, coastal geography, and the collapse of marine ecosystems, they need the data out to 2500. They need to understand what happens to human geography when these slow-moving monsters finally catch up to the carbon we've already banked in the atmosphere.
So the supercomputers run the human scripts out for 500 years. And this is where the paper reveals some of the most mind-bending, almost science fiction realities of the modeling process.
This is where things break down.
Because when you extrapolate these scenarios out to the 24th and 25th centuries, you don't just get interesting weather anomalies. The models literally slam into the physical, geological limits of planet Earth.
The extensions reveal the sheer scale of the planetary forces we are playing with. Let's examine the high extension scenario known as HX.
This is the bad one.
This is the timeline where humanity never gets its act together, abandons mitigation, and continues to rely on fossil fuels indefinitely. If the physics engine runs that storyline out into the 2300s, the cumulative volume of carbon emissions required to fuel that simulated global economy reaches an astronomical figure.
How astronomical.
The energy demand is so vast that to fulfill the script, the simulation requires more coal, oil, and natural gas than physically exists in the Earth's proven and probable fossil fuel reserves.
Wait, really? To make the math work, the model has to consume the entire geological inventory of the planet.
Yes.
It demands more hydrocarbons than we physically know how to extract from the crust. It literally breaks the lithosphere.
It pushes right up against the absolute boundaries of extractable energy. And what is truly fascinating is that the exact inverse problem occurs on the opposite side of the scenario spectrum.
With the good scenarios.
Right. Let's look at the optimistic extensions, like the high to low extension or the medium to low extension. To achieve the cooling targets required in those overshoot scenarios over a 500-year timeline, the models demand the deployment of continuous, massive carbon dioxide removal.
Vacuums again?
They require humanity to vacuum billions of tons of carbon out of the air every year for centuries and pump it deep underground. If you run that math out to 2500, the cumulative volume of captured carbon becomes so massive that it threatens to exceed the planet's geological sequestration capacity.
What exactly does that mean? What is the geological sequestration capacity?
It is the physical volume of safe, stable, subterranean pore space available on the planet. You cannot just pump liquid carbon into solid rock.
Right, you need space.
You need specific geological formations. Deep saline aquifers, depleted oil fields, highly porous rock beneath impermeable cap rock to ensure the carbon stays trapped forever and doesn't leak back to the surface or cause seismic instability.
So there's a limit.
There is a finite limit to how much void space exists in the Earth's crust. These extended overshoot scenarios demand so much mechanical vacuuming that humanity might literally run out of empty caves to hide our atmospheric mistakes.
I have to challenge the utility of this. If I'm an engineer looking at these models and I see that a scenario demands more fossil fuels than exist, or requires more empty geological pore space than the crust can provide,
Yeah.
the scenario is physically impossible.
On its face, yes.
It breaks the laws of the planet. So why dedicate millions of hours of supercomputing time and millions of dollars in electricity to simulating a future that geology dictates cannot actually happen?
Because exploring the extremes of an impossible demand is the only way to locate the hidden breaking points of the natural world. These models are not just predicting the weather, they are stress testing the Earth.
Oh, I see.
We are mapping unknown territory. If we program the model to demand an impossible volume of carbon removal, we get to observe exactly how the Earth's biological and physical systems buckle under that strain.
You watch it fail.
We watch the simulated carbon cycle break. We observe the precise threshold at which the Amazon rainforest transitions into a dry savanna. We pinpoint the exact temperature anomaly that causes the Atlantic Ocean currents to collapse. You cannot understand the resilience of a complex system until you push it to failure.
Right.
You have to push the simulation past the red line to discover where the red line actually is.
We break the simulated Earth, so we know exactly how to avoid breaking the real one.
That is the whole point.
And that brings us to the ultimate question of why this methodology, these acronyms, these 500-year simulations, actually matter to you, the listener. Because, it's easy to view this as an esoteric academic exercise happening in the basement of some supercomputing center.
It can feel very disconnected from daily life.
But this protocol is shaping the tangible reality of your life.
It absolutely is. These 7 scenarios form the foundational DNA of global capital and international law for the coming decade. When a national government sets an emissions target that will dictate the kind of car you can buy, they are using the curves from these models.
And the insurance, like you mentioned earlier.
Right. When a massive insurance conglomerate adjusts the premiums on your coastal home, deciding whether you can afford to live there, they are feeding these precise scenarios into their risk algorithms. When a global asset manager shifts billions of dollars out of traditional energy companies and into green tech startups, they are basing their long-term viability forecasts on the math generated by ScenarioMIP 7.
This paper is the scaffolding of our future financial and political reality.
Yes.
And as we wrap up this deep dive into that blueprint, I want to leave you with one final, deeply unsettling paradox hidden in the methodology of these models.
Yeah, this is a big one.
It's a detail regarding how the socioeconomic screenwriters are instructed to write their scripts. When they build the storylines for the high, the low, and the very low pathways, they are given a specific mathematical instruction to prevent what researchers call double counting.
Right.
The integrated assessment models are instructed to intentionally exclude the physical impacts of climate change on human society.
The socioeconomic baseline assumes a pristine, untouched economy.
It is staggering when you grasp the implications of that. The models that calculate our ability to achieve the very low scenario, the scripts that predict our capacity to rapidly transition the global energy grid, to plant millions of acres of trees, to invent and deploy magical carbon vacuums, and to continuously grow the global GDP to fund it all, are operating in a simulated human world where extreme weather does not damage the economy.
They are completely isolated from the damage. The economic models assume that as the global temperature rises to 2 or 3 degrees, Category 5 hurricanes are not wiping out the coastal factories manufacturing the solar panels. They assume that multi-year megadroughts are not crashing global agricultural yields, starving populations, and triggering mass migrations and geopolitical wars. The simulated GDP continues to hum along, compounding efficiently, generating the trillions of dollars needed to fund the green transition, completely blind and unbothered by the collapsing climate around it.
The blueprint for our salvation assumes a perfectly stable, wealthy, and cooperative human society. Think about how difficult it is to build a massive infrastructure project today. Now imagine trying to build a global fleet of carbon-capturing power plants while simultaneously fighting off the worst weather humanity has ever seen.
It's a daunting thought.
If you were writing that choose-your-own-adventure book and you finally flip to the page that saves the Earth, you might find that the page is already on fire. The models show us the boundaries of the plausible, but the map itself is drawn on shifting, burning ground.
It is the ultimate diagnostic challenge. We know the destination we need to reach, but the vehicle we are driving is taking damage with every mile.
We will leave you with that to mull over. Goodbye for this deep dive. Heliox is produced by Michelle Brucker and Scott Bleakley. It features reviews of emerging research and ideas from leading thinkers, curated under their creative direction with AI assistance for voice, imagery, and composition. Systemic voices and illustrative images of people are representative tools, not depictions of specific individuals. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other episodes, responding to the content, and checking out our related articles at helioxpodcast.substack.com.